share your slide, please. Slides.
Okay.
Yeah, we can see your slides. Yeah, it's perfect.
Okay, so I'm Mariana Araújo from LIP in Portugal. I'd like to thank the organizers for inviting me to give this presentation, which is on the work my team and I developed on understanding Quarkonium production through global fit analyses of LHC data. There are a lot of questions about Quarkonium production, starting with the early 90s when CDF measured GIPSI and Psi2S PT differential cross sections and found that they were about 50 times larger than was expected in the color singlet model of the time. The NRQCD approach was developed, which adds a series of color octet terms with phenomenologizations, which are the LDMEs, and with this new model, the production cross-section could be described. The results for the fitted LDMEs implied that the Quarkonium should have transverse polarization and high PT, which wasn't seen in the data. And actually more than that, the data results measured at the tevatron actually mutually excluded each other. So there was a need to improve the data measurements. So a series of papers were produced to develop better analysis methods, which were applied in the high quality LHC data to obtain a set of polarization measurements for charmonium and bottomonium. And these results all definitely excluded strong polarizations up to the highest probe PT values. CDF also produced new upsilon polarizations using these improved measurements, and these were also consistent with the LHC results of weak polarization. So with this new, more precise and more validated experimental data, this polarization puzzle became even more puzzling. So you can see that still the theory and the experiment were having difficulties. So in order to solve this Quarkonium polarization puzzle, we have to start by understanding that this prediction of a strong inverse polarization doesn't immediately result from NRQCD. It's the outcome of the fits that are performed to the experimental measurements of the Quarkonium production cross-sections. These fits weren't correctly made, and that's what gives rise to these biased results. So how is Quarkonium production treated in our NRQCD approach? Well, in NRQCD, several production mechanisms are foreseen for each Quarkonium state. What is produced in the first hard scattering, and which determines the kinematics and polarization of the final state, is a pre-resonance quark-antiquark state with any combination of colors and quantum numbers. This determines the short distance coefficients containing the kinematic dependence. In a second step, there is a long distance evolution to the observed neutral bound state with fixed quantum numbers, the Quarkonium. And this gives rise to the long distance matrix elements, which are constants obtained through fits from data. The production cross-section for the Quarkonium state will then be a linear combination of these terms over all configurations in angular momentum and color of the pre-resonance contributions. Approximations like the heavy quark limit and calculations of the SDCs lead to hierarchies and links between the pre-resonance contributions that make some SDCs negligible in terms of comparing to the others. And in the end, from all of the possible pre-resonant contributions, we end only with a handful contributing to each final Quarkonium state. So here you can see the kinematic dependence of the dominant short distance cross-section contributions for the main Quarkonium states. So in NRQCD, we expect a mixture of these different pre-resonance contributions with rather diversified kinematics, and each contribution with its characteristic polarization. By fitting the measured PT distributions, the LDMEs of each term are determined, and these are what predicts the polarization. So as you can see, it's a very delicate procedure. So let's take a pedagogical look at a past fit. So this is a fit to CDF data of JPSI production cross-section. As you can see, by comparing the fit function to the data points, the fit quality is very poor. There's a clear pattern in the deviation between the data points and the theory function. But at the time, the fit was actually considered very good. This is because this inconsistency between theory and data was hidden by the application of an a posteriori theory uncertainty band that comes from scale variations in the determination of the SDCs. This isn't a fit uncertainty band. It's not something that contributes to the fit itself. It's just applied after the fit has been performed. And this kind of fit implies for the polarization that at high PT, it's the transversely polarized 3s1 and 3pj octet terms that dominate, and the unpolarized 1s0 term is only a correction. So let's take a small detour through the polarization dimension. The Quarkonium polarization is characterized by the lambda theta parameter. This is experimentally, it's measured as the polar anisotropy of the decay dilepton angular distribution, and in theory, it's calculated from the transverse and longitudinal cross sections. Each color singlet and octet term will have a specific polarization associated, from 0 to plus or minus 1, and even sometimes in physical values that only become physical in the final combination of contributions. So a fit that determines a dominance for the 3s1 and 3pj octets will imply a lambda theta of approximately +1 for the high PT S-wave Quarkonia. And this is what leads to the NRQCD prediction of a transverse polarization at high PT. But actually, if we stop and just look at the high PT behaviors, so we consider the curves normalized to the data for PT over m bigger than 3, it turns out that in this range, the unpolarized 1s0 octet is the term that has the shape most similar to the data. And actually what we find is that if we impose a minimum PT over m, as we increase it, the fit quality improves dramatically until it stabilizes around this value of 3. At the same time, this cut makes the 1s0 octet LDME become dominant compared to the 3s1 octet, which in turn leads to the polarization, taking small values that are much more compatible with experimental measurements. So it turns out that the cross-section polarizations can be simultaneously and consistently described. For PT over m bigger than 3, we have stable fit results, with the polarization and cross-section data both implying dominance of the 1s0 octet term. So in fact, what we have here is a low PT SDC problem. Essentially, the SDCs used in most theory-driven analysis of the data aren't valid in the low PT region. So of course, if we fit the data with the wrong fit model, necessarily we'll obtain wrong fit results. In this case, the Quarkonium polarization puzzle. For example, looking at the production cross-section of the upsilon, it becomes very clear that at low PT, the data has a turn down that is not evident, that is not seen in the theory. So the conclusion here is that the transverse polarization expectation isn't a first principles NRQCD prediction, but instead it's the result of fits that are biased by the inclusion of data at too low PT. So given these issues with previous theory of fits, what we considered was a completely model-independent fit. So we did a simultaneous global fit to mid-rapidity differential cross-sections and polarizations of the charmonium states, the psi and the chi-Cs 1 and 2. In this fit, we accounted for the momentum and polarization transfer from the mother to the daughter particles in all the relevant feed-down decays, from psi to S to chi-C and J psi, and also from chi-C to J psi. For the momentum propagation, we determined that PT over M of the mother is the same as PT over M of the daughter. And for the polarization propagation, it was calculated in the electric dipole approximation. Now, the most important part of this fit is that we don't use anywhere in the analysis any perturbative calculations of the production kinematics. So this fit is exclusively based on an empirical parametrization. So how is this parametrization determined? Well, the J psi and psi 2s directly produced cross sections are fitted as a superposition of an unpolarized and a transversely polarized process weighted by a fractional contribution of the polarized process, the FP fraction. The two processes are given by shape functions, which are power laws in PT over M. And we consider that these two psi states have identical fractional contributions of the polarized process and shape functions. So for the unpolarized and polarized cross-section contributions, we determined that the parameter gamma is the same, but that the parameter beta will be distinct for each of the two. And of course, the shapes and relative contributions of these cross-sections will be constrained by the polarization data also included in the fit. Meanwhile, for the chi-C1 and the chi-C2 cross-sections, and consequently their feed-down contributions to the J psi, we parameterize them independently from the direct psi terms, and we don't separate the polarized and unpolarized contributions, as this study was made before any chi-C polarization measurements were available. So in the end, we have 4 contributions to direct Quarkonium production, coming from the unpolarized and the polarized psi terms, plus the chi-C1 and chi-C2 cross-sections. Altogether, these are characterized by a single gamma parameter and 4 betas. So aside from the main part of the fit, there are also several things that have to be taken in consideration, particularly the dependence of the detection acceptances on the polarization, which is a crucial source of correlation between all the points being fitted. So essentially, for each set of parameter values considered while the fit is running, the expected values for the polarizations and cross-sections are calculated for all states as functions of PT. The values obtained for lambda theta can then be immediately compared to the measured ones, but for the cross-sections, we first have to scale the measured cross-sections by acceptance correction factors, which are calculated for the polarization value under consideration. These corrections can be computed using the tables that are published by the experiments for the cross-sections of particles produced with fully transverse or fully longitudinal polarization. And in fact, that's exactly why these tables are produced, so that these corrections can be applied in studies of the data. So for an example on how deeply the assumed polarizations affect the measured cross-sections, I show here the chi-C2 to chi-C1 cross-section ratios measured by several experiments. So in these plots, we compare the ratio for 2 different polarization hypotheses. And as you can see, not only do the patterns of the cross-section change for the hypotheses, even the levels of agreement among data sets change for different hypotheses considered. So as you can see, the polarization and the correction that must be applied because of it are very important elements of any experimental analysis. Aside from these, there are also nuisance parameters from 2 sources, the luminosity uncertainties of ATLAS and CMS, and also the uncertainties of the branching ratios used by the experiments to derive the cross-sections from the measured values, which are typically branching ratios times cross-section. So this is what we obtained for the fit results. There are 100 constraints and 20 parameters, the 5 shape parameters, gamma and betas, the 4 normalizations for each of the directly produced states, the polarized fraction, and then the 10 nuisance parameters. So the results are compiled in these 2 plots on the right for cross-section and polarization. And as you can see, the fit model matches well with the data with no clear tensions, and the normalized chi-square is very small. And you can see also that the direct unpolarized term of the S-wave states in green is dominant compared to the direct polarized term in red. So actually, aside from this, we also find that the chi-C1 and chi-C2 PT over M distributions are very similar to the unpolarized term that dominates psi production. The beta values obtained for each of these are pretty much compatible within uncertainties. And this very clear observation reflects the fact that we take into account the full chain of feed-down decays so that the high precision psi data points contribute to the precision of the chi-C results. And as I mentioned, the polarized term has a weak contribution so that the charmonium states are nearly unpolarized. Another very interesting result of this fit is that if we take the shape functions from the global fit, which are given by these data bands, and compare them with their NRQCD counterparts, we find over the 8 orders of magnitude ranged by the functions that the NRQCD functions reproduce well these PT over M distributions within the uncertainties. And particularly, they reproduce well then the fact that they seem to be their similarity, so their universality. And so you can see here the comparison between the unpolarized data function and the 1s0 octet. Also for the polarized contribution and the 3s1 octet, and also for the Chi-C1 and 2 functions compared to the sum of SDCs in their that contribute to this state. And as I mentioned, these data bands and next to leading order SDCs are obtained in completely independent ways. So the fact that they match so well is truly impressive. So given that we've seen this good success for NRQCD, we look into its other predictions, and we find that there's also a very strong prediction coming directly from NRQCD, which is that within this framework, the production of Chi-C1 and Chi-C2 has two terms, so that a single parameter R given by their ratio will determine both the yield ratio of the Chi-C2 over Chi-C1 and also the independent polarizations of the Chi-C1 and of the Chi-C2. And so if we take the Chi-C2 over Chi-C1 cross-section ratio measurements from ATLAS and CMS, and we apply the acceptance corrections, which, as I mentioned, depend on the lambda theta parameter, the measurements agree better with each other and with the theory fit if the polarizations are very different. This leads to a prediction for the Chi-C1 and Chi-C2 polarizations that the Chi-C1 is transverse, the Chi-C2 is longitudinal, and their difference can be of the order of 1 at low PT over M. So for another pedagogical study, let's look at the comparison between two different predictions for this R parameter. So Faccioli et al. Derive the R as 0.217 plus minus 0.003. This is obtained from CMS and ATLAS data with the acceptance corrections corresponding to the final polarization prediction, so that this is an iterative procedure repeated until the results converge. So in this case, no added polarization uncertainty is included. The polarization variations are used as an ingredient in the study. Meanwhile, Shao et al. Also derived the value of R, in this case of 0.27 plus minus 0.06. This was from CDF or CMS data with the following procedure. So for CDF, the central values used lambda theta of 0.13 plus minus 0.15 for the Chi-C1 and Chi-C2. No correlation variations were considered, and the polarization uncertainty was added in quadrature with all the others. Meanwhile, for CMS, the central values is lambda theta of 0, and the polarization uncertainty was determined from the maximum range of correlated variations of lambda theta of Chi-C1 and lambda theta of Chi-C2. And as you can see from this plot on the left, the data uncertainty becomes very large exactly by the addition of the polarization uncertainty to all the other uncertainties, rather than treating it as an element of the fit. So in the end, if we compare these two predictions, we find that with the same theory inputs, but different analyses of the experimental data, we end up with very different determinations of R, not only in the uncertainties, which are a full order of magnitude different, but even in the central values. This shows how crucial it is to rigorously treat the correlations between the cross-sections and the polarizations, and to properly account for the uncertainties. The cross-sections depend on the polarization, but that isn't an experimental uncertainty to be added to all the other uncertainties. It's a correction that has to be applied to the values themselves. So actually, it is possible now to test this prediction, because this year the CMS experiment made its first measurement of the Chi-C1 and Chi-C2 polarizations. In this case, we measured the ratio between the cosinus theta distributions of the dimuons associated with the Chi-C radiative decays to J psi. And this distribution provides a constraint on the difference between the polarizations of the two states. So since we have a measurement of the difference, in order to compare with the prediction, we fix lambda theta of Chi-C1 to the predicted value and look at the lambda theta of the Chi-C2. And as you can see from the bottom plot, the data is in good agreement with these predicted polarizations that are quite strongly non-zero. However, the uncertainties we find in this case are quite large. So is it possible to obtain a more precise derivation of the Chi-C1 and Chi-C2 polarizations? The answer is yes, it is possible, because we also have the indirect experimental constraints. ATLAS and CMS measurements of the charmonium cross-sections, together with the charmonium S-wave polarizations, also constrain the sum of Chi-C1 and Chi-C2 polarizations. So by combining the direct and indirect constraints in a fit, using the parametrizations described previously, with no theory ingredients, we're able to obtain results for the Chi-C polarizations. So the only assumption in this fit is that the directly produced J-psi and psi2s states have identical polarizations as a function of Pt over m. And as you can see here for the plots for the results of the fit, again, we find very good agreement between the fit model and data with no clear tensions. So with the combination of these two orthogonal experimental constraints, both on the difference between the Chi-C polarizations and on the sum of the Chi-C polarizations, we're able to determine the two individual Chi-C1 and Chi-C2 polarizations through a purely experimental procedure with no theory involved. In the end, we find for the Chi-C1 a polarization of 0.55 plus minus 0.23, and for Chi-C2 minus 0.39 plus minus 0.22. So the J-psi mesons from Chi-C1 and Chi-C2 decays are respectively transversely and longitudinally polarized, so that they tend to cancel each other in their contribution to the J-psi polarization, and also contribute to this small J-psi polarization that has been measured before. So through this global fit of all charmonium data, we also obtain some results as a function of Pt, for example, for the individual Chi-C1 and Chi-C2 polarizations. So you see here the comparison between the narrow bands obtained from the NRQCD prediction using the R parameter that I showed you previously. And these are compared with the wide bands, which are the result of the global fit with the charmonium cross-sections and polarizations without any theory input. And as you can see, the NRQCD predictions agree perfectly with these two measurements. This is an out-of-the-box success of NRQCD in the first measurement of strongly polarized Quarkonium states. We're also able to determine the directly produced J-psi and psi2s polarizations. And for this, we find unpolarized, pretty much not PT-dependent results with an average polarization of 0.04 plus minus 0.06. This is very strong evidence of unpolarized J-psi and psi2s production, which is a big challenge to production models of Quarkonia. It's more and more unlikely that we're just seeing a fine-tuned cancellation of a mixture of subprocesses. And this begins to emerge as a clear sign of the unique nature and production mechanism of heavy Quarkonia. In addition to this, another interesting result of this global fit analysis is the determination of the fractions of J-psi mesons produced from the feed-down decays of the Chi-C1 and Chi-C2. We were able to determine these both as a function of Pt over m and also as central values of 18.8 plus minus 1.4% for the Chi-C1 and 6.5 plus minus 0.5% for the Chi-C2. So we obtained a remarkably precise value for the fraction of the prompt J-psi yield due to directly produced mesons of 67.2 plus minus 1.9%. So moving to the final conclusions, we've seen that the methodology of global fit analysis has a profound impact on the results obtained. The way that correlations and uncertainties are handled isn't a trivial task. Doing it incorrectly can deeply bias the predictions of the fit. The theoretical uncertainties and the way they're handled inside a global fit is a very delicate task, as was testified by the famous polarization puzzle, which, as we showed, was due to the neglected inability of the next leading order STC calculations to reproduce the data at the lowest PT. We addressed this problem with a new method of theory data comparison, where the data fit is made without any theory ingredient, and the comparison can then be done between an unbiased data-only term and the corresponding theory term. And these results actually show a surprisingly good agreement between the next leading order NRQCD and the mid-rapidity data. Meanwhile, the correlated uncertainties are usually neglected in global fit analysis of NRQCD, but they're actually crucial, as was demonstrated by the example of the Chi-C polarizations. Improved predictions using a correct treatment of the acceptance polarization correlation in the Chi-C yield measurements show a very good agreement with the new CMS measurement of the Chi-C polarizations. And that's everything, so thank you very much.
Thank you very much. It was very interesting. You are resolved the problem of polarization. Okay. Just now, questions. Have anything? Questions to I'm waiting.
Yeah.
No.
Oleg Teryaev has a question, so he raised his hand. Yeah.
May I ask? Thank you for interesting talk. Actually, I just one question is I probably missed something. At one of the slides, you showed some inequalities for lambda parameter, which is in fact bounded by positivity that it cannot exceed 1, right? By modulus. And but you write some inequalities for it. Yeah. So it cannot be less than -1, right? Or it's different normalization.
Essentially, the physical polarizations are between -1 and +1, but the polarizations of the pre-resonance contributions can take unphysical values as long as the total combination that leads to the final Quarkonium state is physical.
So this means that here the positivity bounds for density metrics are violated, right? Because this comes from positivity of density metrics. So this means that this you say intermediate values violated, right?
Yes.
Which is a bit strange, because finally the color octet matrix element are in fact the matrix element squared, right? So they are positive, and generally they should not be violated. Long ago, with Avtot Kabladze, we addressed this issue of positivity. And okay, but maybe it's really, if it is not affecting the final result, maybe this is really not.
Yeah, it might be an issue of the order at which it's calculated, and should go away at higher orders.
Although maybe I would really ask, maybe it's possible still to keep such important property as density matrix positivity also in some intermediate stages. And my question, just another one. You showed two different results for R parameter, right? Which differ within errors. And my question is the following. Maybe you already, maybe somehow I missed it. Isn't you performed very serious statistical analysis? Isn't it possible just to check the property, which is here written explicitly at the top, that really the ratio and polarizations are described by one parameter? Is it possible to check, if to consider this as a sort of hypothesis? Isn't it possible from the data to check the validity of this hypothesis, not fixing the parameter? And what is the statistical significance of this property that R and polarization and are described by same parameter? What I mean is a sort of sum rule, right? Relating polarization and ratio.
I'm not sure I fully understand your question.
I mean, you express R in terms of polarization and the same parameter in terms of the ratio of cross sections. So it seems possible to exclude R from this relations and have just relations between just observables. And my question, I really don't know, but maybe it's possible to check this relation between observables with excluded R and check it how it is statistically valid.
Can I try to answer? I think this is Carlos. I think Mariana has shown that if the value of R is extracted from the ratio of Chi-C2 over Chi-C1 cross sections and used to determine immediately univocally lambda theta of Chi-C1 and lambda theta of Chi-C2, you get these two bands, the green and the yellow bands at the bottom. And then when you go to the next slide, the one that shows the CMS data, the determination from the indirect measurements and the direct measurements, so the the sum and the difference, you see this is what you get from a data-driven analysis. There is no theory at all. There is no R factor at all here.
Yeah.
And then you go to the next slide and you compare the two results. So you see here again the green and the yellow bands. This is the R.
Yeah.
And the bigger bands is the data from all data available in the world on charmonium production, J-psi, psi-prime, chi-c, polarization, cross-sections, and so on. So the fact that the two things agree with each other means that this R does a good job. So the R being the ratio of these two color octets does a very good job in describing the data.
Yeah,
what you are saying is that what if we would derive from the bands the R factor, and you can see from here that you will probably get something which will be in very good agreement with the ratio of these color octets.
Probably, and I just mean, so it looks like there are already quite a lot of data, a great job is done, so maybe it's possible really to test the, I would say, this would be direct test of color octet, right? So if you just write a sort of, somehow something like sum rule relating these two and say, okay, this sum rule is valid up to accuracy, I don't know, 10 or 1% or so. So maybe it is difficult, but it seems to me that it is already, as you described, really, thank you very much. It is already contained here. So maybe maybe it's sufficient for expert, it's sufficient these representations.
Oleg,
Okay.
anyway, I'm sure that you will remain in the session until the end for the discussion session. So if need be, we can come back to that at that moment.
Okay, thank you.
Okay, I think it's enough to discussion. Just now, the